Hello everybody, welcome to the MIT Category Seminar. Today we have David Spivak, MIT, you probably all know him. He's gonna talk about polynomial functor, giving a follow-up talk to the talk he gave last time. Hi David.
Hello, hi Paolo. Great, yeah. So I'll be talking about polynomial functors, and it's just a category that I really love, have fallen in love with over the last few months. So I just want to tell you more about it. And I won't assume you remember anything from last time, although I'll recall everything I need. Yeah, so Kant in his Critique of Aesthetic Judgment says that a person who describes something as beautiful insists that everyone ought to give this object in question his or her approval and follows suit in describing it as beautiful. So in other words, we're suitors for agreement from everyone else. So that's how I feel in this talk. I want to tell you how great this category is. Okay, so the virtues of poly. First of all, it's easy to get people introduced, kind of. It starts with basic high school math. You have y plus 1 times y plus 1 is y squared plus 2y plus 1. The objects of poly are just polynomials. And I use y instead of x because everything in here will be a polynomial in one variable, y, but the y is going to stand for Yoneda. So that's where that y is coming from. So it's somewhat easy to kind of introduce people to this thing, but instead of just arbitrary, instead of just numbers there, we can have arbitrary sets in the exponents and in the coefficients. Second of all, poly is really easy to implement in a dependently typed language like Idris. So I learned Idris, the basics of it, and you can immediately start programming poly because of what poly is. If you've heard of the theory of containers, it's exactly that. But the point is, it didn't take long to be able to actually code up examples and run them. Third thing is that it can be used to model mode-dependent dynamical systems, which I'll talk a little bit about. I talked about it more last time. That was a subject. I'll talk about it a little bit more this time. Basically, the idea is wiring diagrams or string diagrams that can change through time. Think about like atomic bonds that, based on the states or the positions of the atoms, can break or form, or human communication channels that can break and form. The wiring diagram themselves are changing in time. And finally, it has a laundry list of formal properties that I find really amazing. So it's a really rich categorical setting in which to work. Okay. So in this kind of dynamical system point of view, you could think of a Turing machine as two dynamical systems with a fixed interaction pattern. There's a processor. Can you see my cursor? Okay, yeah. So there's a processor, and that has maybe a finite set of states, and it's getting in this value, either 0, 1, or blank from the tape. So inside this wire is transferring 0 or 1 or a blank, and the processor is taking that and updating its state and sending out a command, either an L or a move left or move right, and print a 0, print a 1. And then the tape is being exported, to the environment through this wire. That's just a function from the tape, from the integers to 0, 1. But the point is that this is a fixed interaction pattern. The processor and tape never change their relationship. Whereas in the real world, many systems do change their interaction pattern. Like you might have a company that at one point takes from one supplier, and then after something happens, they get supplied by a different supplier. And so that's the sort of thing that polynomial functors as a setting for dynamical systems make sense of. And that's what the subject of my March 5th talk was. And I'll have links to all my references, including that at the bottom. So, right, last time I talked about poly as a category and its relationship to these generalized lenses things that David Jas Myers talked about in a recent talk. And as a model for mode-dependent dynamical systems. And in particular, at that time I talked about 3 monoidal structures on poly. You can add polynomials, like y plus 1 is y plus 1. You can multiply polynomials, y times y plus 1 is y squared plus y. And there's tensor also, and I'll recall tensor soon. And I talked about how they were useful for combining systems, for putting series and systems in parallel and stuff like that. But I avoided talking about this last and fourth, I don't know if it's the last, there may be other monoidal products, but this fourth monoidal structure, circle, because I didn't know what it did in terms of dynamical systems. And I didn't know much about it at all, except that you can compose polynomials, and that's an easy thing to do, and maybe, you know, it does something. But it's got some real surprises. And so I'm calling them the 7 wonders of the composition product. Yeah. So I want to acknowledge that some of what I'll present here comes from separate conversations with Richard Garner and David Jasmyers. Okay, so I'll discuss some just categorical virtues of poly. And then begin talking about the circle composition product. So what is poly? By poly, I'm going to give 5 equivalent definitions. One is the free distributive category on one object. So you take one object, you multiply, you allow arbitrary small products of it, and you get all these representables, and then you take small coproducts of those and you make them distribute, and that's polynomial functors. So it's the free distributive category on one object. It's the full subcategory of all functors from set to set, spanned by the functors that preserve connected limits. So polynomials preserve connected limits. They're the only functors from set to set that preserve connected limits. And the natural transformations between them are the morphisms. Or you could say it's the full subcategory of functors and natural transformations spanned by coproducts of representables. Or you could say, using what David talked about last time or a few times ago, the generalized lens category associated to the self-indexing that takes from set op to cat that's given by slice categories. So you could take this functor here and apply a certain thing to it that David talked about and get poly. And the fourth, so the one I'm going to use the most is the third one, coproducts of representables, and the fifth one. They're equivalent. The fifth one says that an object in poly is a set S together with a functor from S to set, like a typed set. So every element of S gets a set. And a morphism is a function from one set to another and a collax map back. So in other words, it's a function from S to S prime. And for every element of S, you get a function from the type of f of S to the type at S. So it's kind of this F-sharp pair. A morphism between one polynomial and another is this F-sharp. And from the point of view of, there's a way that this generalizes something called lenses, and F might be called the view, and F-sharp might be called the update from that point of view. So anyway, there's lots of ways that you can think about poly. But today I'll represent objects in polynomial as polynomials. So what's going on here? For every set S, there is a functor set S comma blank represented by S. It's covariant functor, and I'm going to denote it by y to the S. So it's functions from S into something, and the y is a variable standing for a set. So as a functor, y to the S sends x to the set of functions from S to x. But an arbitrary object in poly is a sum of representables, an arbitrary set indexed sum of y to the pi. So a bunch of representables added together. And note that I here, this little I, this index, is p of 1. Because if you apply 1, if you plug 1 in for y, then all of these terms just become 1, and you just get the sum over I and I of 1. So instead of writing I from now on in this index, I'm just going to write p of 1. By the way, these slides will be available online, or they already are. So I've written the slides in a kind of style where they're almost like a paper or like notes. Okay, so the morphisms are natural transformations. And Jules Hedges has this category of bimorphic lenses, if you've heard of it. It's, people talk about it a lot in applied category these days, applied category theory. It's the full subcategory of poly spanned by the monomials. So polynomials that are monomials are those where all the powers here are the same. Right, so there would be called view and update. Okay, and the first kind of nice thing about poly is that the coproducts and products, as I said, are the standard 0, +, 1, and times. So we don't have to worry. It's well structured so that your intuition is working. So these are two monoidal structures on poly. There's plus and times, co-Cartesian and Cartesian, but there are at least two more. I only know of two more. One is the Dirichlet product. So before I introduce the Dirichlet product, I'll show you how I'll make it analogous to the regular product here so that you'll understand kind of what's going on. So if you want to multiply two polynomials, you choose an index from each, and then you multiply the two powers, and the powers add. The Dirichlet is almost exactly the same, except the powers multiply. Okay, so this is the Dirichlet product, same exact formula, except multiply powers. And we said when talking about dynamical systems, this is what lets you put two boxes in parallel, or put two boxes into a bigger box when you're putting the Turing machine together or whatever. So tensor is a third monoidal product. Its monoidal unit is y, and it distributes over plus. And I should mention that both times and tensor are closed monoidal structures. So there's like an exponential and another internal Hom that come to you that are right adjoint to tensor and times. And they have these formulas for whatever they're worth. I'll leave them there, but we're not going to need them.
David, is that J
Oops.
Q of 1?
This J is Q of 1, and this J of Q is Q.
And that
Q.
I in the indexing is J?
And the I in the indexing is J. Thanks, David. Sorry about that. Okay, the fourth monoidal product is circle. It's that you can compose two polynomials, and that is functorial in both. It is not symmetric, the other three are. And so, that's interesting. And we'll spend most of the rest of our time talking about circle. Composition product, I'll call it. But before we get there, just a few more formal structures of poly. There's an adjoint quadruple from set to poly. Every polynomial has a constant term, p of 0. That's right adjoint to the functor from set to poly that makes a set a constant polynomial, like 5. That's itself right adjoint to the functor from poly to set that returns the p of 1. In other words, the kind of summands. And that itself is right adjoint to the functor from set to poly that returns the linear polynomial, like 5y. And there's also an adjoint functor between adjoint functors between set op and poly. There's a representable, and there's something you might call the global sections of a polynomial. It's kind of a strange construction from polynomial point of view, maybe, but it's actually this function, it's polynomial maps from p to y. So it's maps to the monoidal unit of circle or tensor. A little bit more about poly. There is a functor from poly to set that I've already said. It's p goes to p of 1. And it's what Mike Schulman calls in his frame bicategories paper a monoidal star bifibration. And what that means is that if you're not familiar with fibrations, basically this map from poly to set that you get by plugging in 1 gives you a kind of control panel on polynomials where your controls are in set. So you have your set p of 1. If you have a map to it, you can move p back along that map to some other set. So if you have a map from A to p of 1, you can move p back to the fiber over A. And similarly, that operation, which you could call delta f, has both a left and a right adjoint. There's an op here, so it's a little bit different than you might think, but there's both a left and a right adjoint called pi f and sigma f, and they let you move forward along the set maps. If you're used to polynomials not in one variable, but in many variables, then the usual polynomial functor can be expressed completely within poly using this monoidal star bifibration as this thing, as you'd expect. So there's a lot of control we have over poly. We have, let me just say, there's a vertical Cartesian factorization system coming from this, and we will use this a little bit later. So the only part I'm going to use is what Cartesian means a little bit later. So a map of polynomials, f sharp, f is like the view and f sharp is the update, or F is on the summands and F sharp is on the exponents. Vertical means F is an iso. So it's an iso on that part. And Cartesian means that each Fi sharp is an iso. So it's an iso on the exponents. So all 4 monoidal structures preserve Cartesians and all 3 symmetric ones preserve verticals. Okay, so the first wonder of composition product is that it interacts really nicely with plus, times, and tensor. And maybe this is a bit mundane. Maybe I just wanted it for to get 7, but oh well. So so commutation on the left with plus and times. I mean, you know how to compose functors or functions. If you compose with a plus, it's the plus of the composites. And if you compose with a product, it's a product of the composites. And that only works on the left. Okay. But here's a slightly more interesting one, and we're going to use this one later, is that there's a duoidal interaction between circle and times or plus. So the plus one just comes from the universal property of plus. Every monoidal structure would have this property. You can take this coproduct of P1 and P2 and move it into this circle composition. But the more surprising one, I guess, nothing surprises Richard Garner when I talked to him about this. So he explained this to me, but I'll just leave it at this. I was surprised that there is this. Actually, no, I think it's purely formal, and you can even find it on the NLab that there is this other duoidal interaction here. But the plus one helps me remember the form of the tensor one. Is it tensor inside and circle outside, or is it circle inside and tensor outside? Well, it's the one that's like plus. Okay, so okay, maybe this one isn't as exciting as the ones I want to tell you about, but I want to just summarize by saying that Poly has a lot of great structure. 4 monoidal structures, 2 closures, duoidal, all sorts of interactions. So the 7 wonders I'm going to talk to you about are, well, it interacts really well with these other 3 products. I'm going to tell you about relationship to strategies in the sense of kind of game theory. I'll talk about speeding up dynamics. I'll talk about how you might think of this as a kind of generalization of coalgebras, or using comonoids to generalize coalgebras. I'll talk about how Cartesian monoids are operads. This is a result of Gambino and Kock. I'll talk about how comonoids are categories. This is Ahman and Uustalu. And I'll talk about how bimodules are parametric right adjoints. And this is Richard Garner. So the rest of the talk is just me explaining 2 through 7 in order. Maybe I should pause quickly for questions.
Yeah, we do have some questions. So, okay, somebody's asking, what does Poly not have that SAT has?
Poly is not a topos. Poly doesn't have exponentials. Is that good? Poly doesn't have a, wait, Poly, sorry, what am I talking about? Poly does have exponentials. Poly does not have a subobject classifier.
Okay. And then we have 2 more questions are in the chat, but they probably refer to something that you said earlier. So could you people please clarify the context of your questions in the chat? Christian Williams and Samuel Tenka.
Sorry, I was just surprised that
I'm also surprised.
The formula for the closed structure and for times and tensor involved the circle.
Yes, they do involve the circle. But you don't need any explanation right now, I guess.
No, yeah, it's okay.
Yeah.
Okay.
Okay, so
Samuel
I'll move.
Tenka is then asking, David, show us that there are lots of adjunctions between SAT and Poly. Are those all that you found?
No, there's also P of n for any n is adjoint to AY to the n, I believe.
Okay, that sounds.
I'm naming things by where they send A and P, by the way.
That sounds like what they were asking. Like they were asking if they increase in degree from constant to linear,
Yeah, they do.
and then it continues.
Yes. But they wouldn't be in that adjoint quadruple. They'd just be kind of on their own.
Sounds good. And okay, last question. What are the morphisms in poly again? They're asking.
They're natural transformations.
But do they have like an interpretation in terms of like algebra of polynomials?
No, that's the weird. So you can say, yeah, they categorify high school algebra or middle school algebra or whatever, but there's no notion of morphisms in middle school algebra. The closest thing you get is exponentials, like 3 to the 5 power or something. The set of functions from 5 to 3, that generalizes to poly in 2 different ways. But no, there's not, we would never talk about morphisms of polynomials in high school.
Okay, thank you. I think that's
maybe in the future. Okay, so what I want to talk about next is what this composition product has to do with dynamical systems. So the terminology I'm going to use for dynamical systems, and maybe even just for polynomials in general, I'm going to think of a polynomial as a kind of arena for interaction. So here's my polynomial, and the arena has various positions in it where you can be. And at each position, there are various distinctions, what you can see there. So you're in this weird arena. Maybe it's your body, or maybe it's some kind of place to do something. And there are various positions you can be in. And that would include your outputs. So if I'm talking, it's because my tongue is in various positions. So it's a very general sort of position. I might be looking to the left or looking to the right. Those are positions. And whatever position I'm in, there are various distinctions that I might be getting there. And that's the arena. So the position set is P of 1. And for every position I, the distinction set is that exponent P of I. So if the arena is 8 uneta y to the string plus 8y to the bool, there would be 16 positions, and at half of them you'll be noticing a string, and at the other half you'll be noticing a Boolean. So one that's a polynomial that's going to come up a bunch of times is sy to the s for a set S. And there you have a set of positions, and what can you see in every position? You see another position. So it's kind of self-referential in that way. Okay, so given a morphism of polynomials, what is that in terms of arenas? Think of the arena P being like an internal world inside of arena Q. Like there's a little self inside of yourself or something that's really making the decisions. Then that little self would be the P, and your body would be the Q. Or if you're the decision maker for an organization, then maybe you'd be the P and the organization would be the Q. So every position you have is externalized as a position in this bigger arena Q. So that's F of I, that's the F, what people call view in lens theory. And then every distinction in the big arena at the position it thinks you're in is internalized for you as a distinction you're making within in your little world. That's the F sharp. So those are the morphisms in polynomial, in poly. They're this externalization of position and internalization of distinction. And so, for example, if we call S the set of states, and you look at a morphism from sy to S to P, a polynomial P, then every internal state is externalized as a position. So this is how you read out your internal state as a position. And every distinction available there, it's like an input in that position, you would input it or internalize it and get a new state. That's you updating your state. So what does circle mean in this context? I want to rewrite a polynomial like this by taking this exponent and writing it as a product. So P is the sum over I and P of 1 positions I of the distinctions available there of Y. And Y is a variable standing for a set because this thing's a functor. And so this says, I'm going to read it as a P position, a choice of P position, and for every P distinction available there, a future. And the reason I'm reading it as a future is because it indicates that this functorial variable Y is an unknown set, and you're getting an element of an unknown set, and that's your future. So if P and Q are polynomials, I'm trying, this whole like future and distinction and position stuff is trying to give intuition for what morphisms and circle mean. And so what does p-composed circle mean? It's, well, it's this formula here. I just plug in q for y. And it says, oh, by the way, the sum ands are always over fixed sets, and the products are always dependent on them. But anyway, what does this thing say, p composed q? It says a p position, and for every p distinction available there, a q position, and for every q distinction available there, a future. Okay, so that's what it says. But now let's look at strategies, as this is number 2, that strategies somehow come up as composition powers of p. So for any polynomial p, p to the power n is a choice of position, and for every distinction available there, a choice of position, and for every distinction available there, a choice of position, and so on n times, and then finally a future. So a choice of, so an element of this thing, of this polynomial, is kind of this strategy of choose a position, then for every kind of choose a play or a move or a position, and whatever you get back, give a choice of move n different times, n times in a row. So in other words, this sort of combinatorial game is baked into the composition product. So one of the heroes of today will be comonoids. And when I mentioned that sy to the s was important, we'll see it come up a few times. What makes it important is that, in some sense, is that it's a comonoid in poly. So this comonoid is well known in functional programming. Instead of thinking about poly as its own category, we might think of the functors from set to set that poly is a subcategory of. And there, instead of calling it a comonoid, you'd call it a comonad. So this would be called a polynomial comonad, and they'd call it the store comonad in functional programming, and it's cousin to the state monad in functional programming. And it's just the comonad that comes from the adjunction of currying and uncurrying. So again, our use of sy to the s when we talked about dynamical systems really stemmed from its comonoidality. The co-unit of this comonoid, in some sense, says stay where you are. You'd have to kind of work it out to see what I'm saying here, but I'm putting in quotes, it means stay where you are. And the co-multiplication delta says make 2 moves in series. Now, one might ask, how should I think about comonoids in poly generally? In fact, I've already answered this, but maybe you've forgotten. I kind of glossed over it. I'll show that soon, and I'll say how to use them in practice. But I'm going to use this comonoidality to speed up dynamical systems. This is the third thing. So when you have polynomials and dynamical systems and things, you think of them as operating in a kind of discrete setting where there's a kind of tick of the clock, and every time the clock ticks, this thing takes in a new input, updates and outputs something. But we're going to be able to speed up dynamical systems using circle. So before I get there, we have this comonoid, any comonoid, and I might write delta to mean the n-fold iterate of delta. So instead of just s mapping to s circle power 2, I could compose that with another delta to get s circle power 3. And if little s was sy to the s, this would mean like move n times in a row. So given any natural number and any morphism from a comonoid s to an arbitrary polynomial p, we can use functoriality of the circle to get a map from s circle power n to p circle power n. And we could precompose that with delta to get a map from little s, the same s as originally, all the way to p circle power n. And this is going to be a new dynamical system, if s is sy to the s, for example, a new dynamical system with the same states, but moving faster, because in every moment, it's still ticking in time with everybody else in the system, but in every moment, it's outputting the entire length n strategy. And that could be combined with somebody else's input and length n strategy that was feeding this dynamical system. And so you can actually have one thing operating n times faster than something else. So we've lost our boundedness to kind of single, to this lowest common time denominator type thing of 1. We're now able to simulate moving n times faster. So let me give an example for differential equations. You don't have to know differential equations beyond this slide, but you might have x dot is f of xa and b is g of x. So x, this differential equation, x could be a d-dimensional, living in a d-dimensional space and inputting an m-dimensional input at just changing through time. And the derivative of x is some function of x and a. And then we're going to output b equals g of x. So I'm just naming x is rd, a is r to the m, and b is r to the n, where x, a, and b live. And this thing, this differential equation, can be encoded in some sense. Whatever encoded means, I can write it as a polynomial map from xy to the x to by to the a. So what does that mean? It means that on positions part, given any position x and rd, I get back a position b. That's what I'm kind of outputting to the world. And given a position in x, in r to the d, and an input a, distinction, I get an updated x plus f of xa, f of x comma a. And that would be what this polynomial is encoding for real. It's not encoding this differential equation, it's encoding this kind of difference equation. And so what, in some sense, you could say is the dynamics of this polynomial is what you would get by doing Euler's method of approximation with a time step of 1. But now, by letting f sub n of x comma a be f of xa divided by n, and using a very similar polynomial, I can speed it up by n. I can do n of these in every moment of time. And now I'm making n many little updates at a time step of 1 over n. And so as n approaches infinity, which I don't know what that means categorically, but analytically, as n approaches infinity, these polynomials sped up n times faster, you would recover the dynamics of the original ODE. So to arbitrary precision, you can get this differential equation occurring through this kind of speeding up process. Okay, now we're moving a little bit from the applied to the theoretical stuff, but this one's kind of halfway in between. So for a polynomial p, a p coalgebra in the sense of Lambeck, not for a comonoid now, but for just a regular old polynomial, a p coalgebra is a set S and a function from S to p of S. So, but that's the same thing as a map in Poly from sy to the s to p. I don't have to think of it outside of Poly. So I can think about this coalgebra without having to leave Poly. And this lets you think, what is it about sy to the s that's really making this work? It turns out that what makes it work is that sy to the s is a comonoid. And so this map sy to the s to p that we started with induces a comonoid map from sy to the s to the co-free comonoid on p. And I've given a formula for the co-free comonoid on a polynomial p. You start with the polynomial 1, you take the polynomial y times p of 1, and there's a unique map there. And then I just take y times p of that and y times p of that over and over again. And I take this direct limit, and that's the co-free comonoid. So if you check what happens when, what are the positions of this thing? This is going to be a polynomial, and polynomials have positions and distinctions. And the positions are what you get when you plug in 1. And if you plug in 1 for y here, you'll see all the y's go away, and you'll just get the usual formula for the final coalgebra, if you know the final coalgebra of a polynomial functor. So you get p of 1 from p of 1 from p of 1, etc. But this is the co-free comonoid, and for any comonoid S, we get this map from S. Given a map from S to P, we get a unique map from S to co-free of P. And it generalizes this terminal coalgebra construction. And we'll see soon that, that the comonoid S here is acting as some kind of historical recorder. And that we'll see later that sy to the s as a historical recorder says, quote, to me, history is just its endpoints. So what's the history of between, I don't know, the founding of the US and now? It is the founding of the US and now. So it's a completely boring history. And we'll see that putting in a more general comonoids records history in a more general way. So in some sense, dynamical systems as coalgebras are machines that record history trivially, but do act. And that might be what you want, but you can generalize it to an arbitrary comonoid instead of s, y to the s. Okay, so now I'm moving to theoretical wonders of the circle monoidal structure. And the first, recall that a map of polynomials is Cartesian if the update part, the distinctions part, is an iso for every position. So for example, if you know what I'm about to say, I'll say what I'm about to say. There's a result by Gambino and Kock that says that we're going to use. And if you're familiar with it, you might be interested. I don't know if this is obvious or not, but probably. The terminal object in Poly with Cartesian maps is this thing here, the sum over all n of y to the n. And this is the list functor. So this is the terminal object in Poly with Cartesian maps. It takes in set x to the set of lists in x. So this result of Gambino and Kock says that the category of one object operads, I'm using a special case of their result. The category of one object operads is equivalent to the category of monoids in polycart. So with this circle composition, so we're supposed to be telling you how great circle is. And what I'm saying is that operads just fall out of polycart with this circle. So the idea here, how's it working, is that P of one, the positions, turn into the operations of the operad, the morphisms, and the PI, the distinctions for every operation, is the set of inputs, or the arity of that operation. The unit maps picks out an operation that serves as the identity, the unit of the monoid, and the multiplication gives the composition structure. Right, so the category of operads is exactly the category of monoids in polycart. So that's pretty neat.
David, can I interrupt you?
Did someone say something? Oh, Joachim?
Yes, so I mean, there should be some finitary condition for this to be true.
Ah. And
also, it would be true over groupoids, but over sets, first of all, it will be only non-symmetric operads, and second, you need to put it over list to make it true.
List is the terminal Cartesian thing.
No.
Yeah. Oh, I'm sorry, you're right. Sorry, everyone. This is the terminal Cartesian thing in finitary. Thank you, Joachim. Thanks for fixing this. So
no, it's still not terminal.
No, why?
Because one thing is that there's a unique map on what you call positions, but there's not a unique map on the distinctions.
The distinctions are the arity.
Well, I'm not completely sure about the terminology, but it's not terminal.
Oh, you're right. Oh, because of the
you need groupoids, you need to divide by the
groupoids. Sorry, everyone. You're right. Yep. Thank you. Thanks, Joachim. Yes, you're right. So I need to worry because there's an isomorphism available. Too much space there. Okay, yeah. Okay, so apologies, everyone. So this is not quite true. Let's bring it down to 6 wonders. But I do recommend this paper and maybe to get the correct result. Okay, so let me move on. So categories are comonoids. We asked above if there's a good way to think about comonoids in Poly, and the answer is that there is. So a comonoid in Poly is precisely a category. The positions, P of one, are the objects of the category. And for each morphism, for each position, the distinctions are the outgoing morphisms. So this was what Richard talked about in his talk, and I'll give a reference at the end. It's actually a result due to Ahman and Uustalu. Right, so for a comonoid in Poly, as I said before, is kind of the hero of this talk. It's a category. The objects are the positions, the distinctions are the morphisms out, and the co-unit assigns an identity to every object, and the co-multiplication assigns codomains and compositions. And I'll explain that in a little bit. I'll explain a bit in a second. Right, and the co-monoid laws turn into category laws. So Garner offers both a highbrow and a lowbrow way to see this. I'll discuss each. I don't know if you'll really call it lowbrow, but a very nice calculation, a calculative way to see this. So to set up the calculation machine, let me say that there's another category equivalent to poly, namely the objects. As I said before, we said that objects are type sets and the morphisms are colax triangles. But you can also think of that as objects are functions, E to B, and morphisms are these pullback square things. So distributivity pullbacks are sometimes called. So it's a map from B to B prime. Then you pull back your E prime along that, and then you'd give it another map F sharp to E. So this is equivalent to the one above, but it's the one that's going to be easier to talk about in the way Richard set things up. So, so as Garner said in his talk, a map from P to a composite of P1 through Pn, for example, say if P is E arrow B and Pi is EI arrow BI, a map here is a bouquet of pullbacks. So it's the n+1 blue arrows. So what happens is, to give a map from P to this composite there, you give a map from B to B of 1. You pull back to get this little bullet here. You give another map F2 to B2. You pull back, you give a map to B3, all the way until the last one, you give a map from the pullback to Bn. You pull back one last time and you give your F sharp. So it's basically the n=1 case is the thing I put on the previous slide. And we can do that for maps from P to P1 through circle Pn. So, and if you want to compose these guys, like if you have another one coming off of this P2, you have some more stuff coming off of it, you would just take a whole bunch of pullbacks. Okay, so there's a painstaking calculation that co-monoids are categories. It takes about 15 minutes or maybe more. I mean, just to kind of calculate a whole bunch of things. You'll find out that the co-unit is giving you the identity, and the co-multiplication, and that forces a certain thing, the F, one of these guys to be identity, and the co-multiplication is giving you the codomains and the composition. So the comonoid laws enforce the necessary equations, and in particular that this is the identity, and so you can kind of make this calculation. The highbrow explanation is that poly is the category of functors from set to set that preserve connected limits. A comonoid in poly can be identified with a set A and a comonad set over A to set over A that preserves all limits. And that takes a proof. But then given a functor from set over A to set over A that preserves all limits, well, it has a left adjoint. So this R gives us a monoid. It was a comonoid. Now we get a monoid from set over A to set over A that preserves all colimits. And a map from set over A to set over A preserving all colimits is determined by its image on the elements of A, because every set over A is a coproduct of elements of A. And what do you get when you apply it to an element of A? When you apply L to it, you just get some L of A over A. You get some set over A. And so we can identify L with a span from A to A. And so we're almost done here. Monoids and colimit preserving functors from set over A to set over A are monoids in span, and monoids in span are categories. So that's the highbrow way of seeing this amazing fact that comonoids in poly are exactly categories. So back to the coalgebra picture, when I made some kind of cryptic remarks earlier about coalgebras, what does comonoids equals categories mean in the setting of coalgebras? Well, a P coalgebra is a map sy to the s to P. And I said what makes it work is that sy to the s is a comonoid. But comonoids in poly are categories. So the question is, what is sy to the s as a category? As a category, it's the contractible groupoid on S. So its objects are S, and there's a unique map between any two objects. So sy to the s is kind of the most boring category in some sense. It's terminal in the category of categories. It's not terminal in the category of comonoids, but it's still a pretty basic category. A more general notion of dynamical system might be a general comonoid mapping to P. And in general, what's going on here is that C, the morphisms in C, keeps track of this internal path history as a morphism. Okay. So if you call Catsharp the category of comonoids in poly, the objects are categories and the morphisms are not functors, they're cofunctors. So comonoid morphisms are not functors. There are these things called cofunctors. They're a map from objects in C to objects in D. And for every object in C, a function from the outgoing arrows of the target thing to the outgoing arrows of C itself. And it preserves identity and composition. So that's what a cofunctor is. These turn out to be what the morphisms between categories are when you think of categories as comonoids in poly. So for example, if you take the co-free category, co-free comonoid on Y, you get Y to the N, the monoid of natural numbers. So a cofunctor from C to N is just the same as a polynomial map from C to Y, which is just a global section. Or another way to think about it is a trajectory. It is a choice of map out of every object in your category. So if you have any category, and let me motivate this by saying there's an adjunction here. There's an adjunction between mon op and Catsharp. And given a monoid, you can take the representable on it and get a category. And the morphisms, the cofunctors will just be monoid morphisms op. And this has a right adjoint. And so that's where this kind of trajectory thing is coming from. What's a trajectory on a category? In other words, it's a map from your category, considered as a comonoid, to Y to the N. And it turns out to be just a trajectory on your category. So for any category, you get a monoid of trajectories. What is your trajectory on a category? It's for every choice of object, a choice of map out. So that takes any category and returns a monoid. Yeah, so anyway, Catsharp is the category of categories and cofunctors, or really, maybe we could just define it as the category of comonoids in poly. It has two monoidal structures that came to us from the duoidal structures of Cirque, the duoidality of plus and times from Cirque. So it has a plus monoidal structure and a times monoidal structure. Plus returns the coproduct of categories. Tensor returns the product of categories, though of course they're not the coproduct and product in Catsharp. They're just monoidal structures there. And finally, the last of these 7 wonders, again, is due to this Richard Garner talk that I'll reference at the end. If C and D are comonoids, which you think of as categories, then a CD bimodule, in the sense of bimodules, like equipment type bimodules, if you think about that, or just bimodules from rings. You have this polynomial M and a map to C composed M and a map from M to M composed D. That's a CD bimodule and satisfies some conditions about unit and co-unit and co-multiplication. And it turns out that these are exactly the parametric right adjoints from set to the D to set to the C. That's an incredible fact. What is a parametric right adjoint if you don't know? Set to the D has a terminal object. And so if you have a functor from set to the D to set to the C, then every object in this guy gets a unique map to 1. So when I apply f to it, it gets a unique map to f of 1. And we would say that F is a parametric right adjoint if F prime is a right adjoint. Okay, so this fits surprisingly well with, there's a story called databases as categories. A database schema is a network of interconnected tables. And the tables have a bunch of columns. Each table has a bunch of columns. Each column of a table points to some foreign table, and there are integrity constraints. And so basically a database schema is a bunch of tables and a bunch of columns, and we can think of it as a category whose objects are the tables and whose maps out of a table C are the columns of C. So if database schemas are categories, then the data itself is a functor from C to set. Okay, well, polynomial comonoids C describe categories in that same kind of way. Categories as databases like to think about the category as objects and maps out, and polynomial comonoids also think about objects and maps out. Coalgebras on C, this is now like Eilenberg-Moore coalgebras, are precisely the set-valued functors. So you can take any set-valued functor from C to set and think of, I of little c is the rows in table C. And so if we add up all those rows of all the tables, then we can encode that functor I as a coalgebra from S to C of S. And so we can think of this as a constant bimodule and then compose it with our data migration functor. Oh, I forgot to say this. Parametric right adjoints are the way you move data. So a DC bimodule, in the sense of in comonoids, gives you a parametric right adjoint. This was Garner's result. And that's the way you move data from instances on C to instances on D, data on C to data on D. So we can actually compose our instance with this bimodule to get the migrated database instance. And that's about it for the talk. So the summary is that Poly is a beautiful category. There's lots of different ways to talk about it and formulate it. It has 4 interacting monoidal structures and 2 closures. It gives you categories and co-presheaves and parametric right adjoints, and with some corrections, it gives you operads. It gives strategies and speeding up dynamical systems and generalizing coalgebras. And I think that Catsharp, this categories and cofunctors, deserves more exploration. I only heard about cofunctors for the first time maybe last summer or so. I think they're obviously pretty neat because Poly is so neat. So it's interesting to think about Poly in terms of dynamical systems and databases. It encodes these mode-dependent wiring diagrams and dynamical systems. It has direct applications to databases. And I wonder how these 2 applications might come together. So that is it. Thanks. And I'll leave up the references, I think. So thank you. And I'll take questions if people have them.
Thank you. Thank you, and thank you for the talk. We have a question. Somebody's asking, what does the semicolon mean? Some sort of Kleisli composition?
Oh, sorry. Well, semicolon, I often mean just composition in the diagrammatic order. I'm not sure where I put it, but oh, this semicolon here. This is composing F and then this thing. And this semicolon is grammar.
There's a comment. Jules saying that Bryce Clark gave a talk at ACT 19 about lenses and cofunctors. Yeah, I remember that too.
Yeah, that's I think where I first heard about lenses and cofunctors was from Bryce.
Yeah, me too. All right. Are there any more questions?
I have a comment.
Go ahead.
That's beautiful, everything. Congratulations.
Thanks.
And then there's a 5th monoidal product, which is the Hadamard product.
Oh, really? Tell me about it.
So on power series, it's just degree-wise multiplication of coefficients.
Mm-hmm. Do you know how it interacts with the other monoidal structures?
I don't remember.
Yeah, wow. Yeah, this thing is just full of surprises and full of stories. It just seems to just want to tell stories all day. Thanks, Joachim.
If I may also comment, there's also a sixth monoidal structure, which is also valid for species, that is more obscure. I'm trying to find the reference now. I'll put it on the Zulip when I find it.
Cool. So Hadamard is symmetric, I guess. And is yours, Jacques, symmetric?
I don't think so. It's kind of a lifting of, it makes things look like matrices.
Cool.
There's also, on species, there's a scuba nodal product, which you can sort of think of in terms of grafting a species at one input instead of, at all in inputs, just at one at a time. And that looks sort of vaguely reminiscent of some of the things you're doing here.
Mm-hmm.
In particular, the SY to the S reminds me of one of the unit constraints that you would find in that setting. So I don't know, I'm just...
Yeah, I'd love, do you have a reference or?
I can give you a reference to some scribblings on the InLab.
Okay.
Todd, is that not a pre-leaf product?
A pre-leaf product?
Pre-leaf.
Pre-D.
Lee, pre-Lee.
Pre-Lee, I'm sorry. I don't know. I don't know that terminology, I'm afraid.
Like LIE or some other?
Yes.
I guess I have a question, which is, of course, you made reference to the container stuff and so on, and where part of that came out of was, Connor has this notion of differentiating a data type, and I know in species how that makes sense. In this setting, I imagine you would have, at least sometimes, you would have a shift operator. And does that shift operator interact in an interesting way with composition or the like?
So in that shift operator, you delete an element, or you choose an element of a set, right? In this differentiation point of view. I don't know if there would be such a thing when you get outside of ordinals, or when you get outside of, yeah, I'm afraid I don't know.
We have two more questions from the YouTube chat. Someone's asking, the Hadamard product is also known as a direct product as opposed to tensor product, right? Or am I confusing this notation with quantum terminology?
Maybe that's a question for Joachim.
I mean, you can embed polynomials into species, and then it's the Cartesian product. So the polynomial functors are the flat species. And the Hadamard product of species is just the Cartesian product.
Oh, okay. So it's just, I think I did mention that one then, I suppose.
No, it's the Cartesian product of species, but not of polynomials.
Oh, okay.
Right.
Okay, there's another question. Folklore says that there are only trivial comonoids in Haskell. Are there non-trivial comonoids in Idris?
So there are only trivial comonoids in Haskell. What that would be in this category, in this talk, I would say there's only trivial comonoids in set, meaning every set has a unique comonoid structure. But we're not living in set, we're living in poly, where there's lots and lots of interesting comonoids. Namely, they're the categories. I hope that answered the question. So Idris allows you to encode poly. And once you do, you can write down what is a comonoid here. and you can, and you'll find that they're the, well, you can prove that they're the categories. You can turn any category into one and any one of them into a category.
What was the coherence for cofunctors? What was the equations required?
So I have a talk, or sorry, I have a paper on the archive called this thing, which puts the conditions in, but it's preservation of identities and composition. So the same sort of thing. It's just that the things that are being preserved are kind of going backwards.
And it was a little surprising to hear that that you can embed poly into species, because it seems like the morphisms of polynomials are, I don't know, weirder than.
Well, they're required to preserve morphisms in set, whereas species are only required to preserve morphisms that are bijections.
Oh, okay.
Sorry, maybe I said something wrong. So when you embed it into species, you only take the Cartesian maps.
Mm.
Oh, okay.
Sorry about that.
You can't change the size of the exponents.
Right.
So we have another question. Is the Idris encoding of poly available somewhere like GitHub?
Yeah, if I don't know if it's public or not, but I can share the repo if somebody wants it. Just have them write to me.
Okay, so if you're interested, please write to David. More comments? So there's one on the Zulip chat with a link, so it's probably better if we look at that directly in the Zulip channel. And instead in the chat here, Jacques has found the product he was mentioning.
Mm.
It's called
And I put it in the Zoom chat, sorry.
Do you wanna talk about it or?
Not really. I'll actually, the best place to read about it, and I'll put it on the Zoom chat, is actually in Brent Yorgi's PhD thesis, where he explains it with nice, pretty pictures.
But it does extend to a monoidal structure on poly?
I don't know. I only know it works on species.
Ah, okay.
So, but, you know, it looks like it would.
Mm. Fun.
Your email address is available somewhere, because I'm currently formalizing species in Agda, so I'm very curious to do poly as well, but of course in my favorite toy.
Yeah.
Instead of your favorite toy.
Yeah.
So thanks.
Yeah, I put it in the chat.
Okay. Anybody has any more questions or any more monoidal structures?
Just one more comment. I think that this Meyer-Mendes arithmetic product is the same as the Dirichlet product.
Oh, in Dirichlet product in poly.
I think so, yes.
Okay.
All right.
That would certainly be cool.
Okay, anybody else? Okay, seems that there's nobody, so if you have any more, please write them in the Zulip channel. We will try to have the discussion offline. And for the ones that want, now we're moving into breakout rooms. So in like 1 minute, we will divide into little rooms and so we can hang out together. Okay.
Great.
For the rest, let's thank David again for the talk.
Yeah, and thanks Joachim for catching the mistake.